Okay. Good afternoon, guys. So to parse the title, diba, we can see that the task is about video. And when it says searching for multi-stream neural connectivity, it gives us a hint that it's about a search algorithm which they'll be presenting. By multi-stream, they mean having different kinds of inputs. And by neural connectivity, how to connect elements, different elements of a neural architecture. Okay, let me just fast forward to contents. Okay. And so early data sets in action recognition were easy in the sense that models only needed to see a frame and they would perform well already. So, for example, if they see something like this, okay, it's skydiving. That's pretty easy. Diving, jumping, and all those things. But later data sets, they're more well complex in the sense that um, you have to see the motion as well. In this frame, for example, the man, you can't tell if the man is opening or closing the door of this, I think, refrigerator. And certain concepts, certain action concepts like opening, now have multiple ideas behind it. So opening could mean the blooming of a flower. It could mean the baby's mouth opening to yawn, or a person opening an object, like this lady opening the box. Okay, in this example. Okay, so video is more complex than image recognition because in video you have to worry about two things now: the appearance and the motion. And in 1992, Goodale and Milner presented a paper entitled Separate Visual Pathways to Perception and Action, where they came up with a two streams hypothesis. So they said that the human visual cortex contains two pathways: the ventral stream, which is associated with object recognition, and the dorsal stream, which is about movement, seeing movement. So this is just a small table here contrasting the two streams. So the ventral stream is responsible for recognition identification, and the dorsal stream for seeing, motion. The speed for ventral stream is relatively slow since it expects objects to be static in space, and the dorsal stream, it acts more quickly because it's paying attention to motion. And so the sensitivity shown here. So the ventral stream is sensitive to spatial details, whereas the dorsal stream is sensitive to changes, things changing in time, or the temporal motion or the temporal differences. Okay, so let me just talk about works on the two stream. In 2015, Simonian and Zisserman presented this paper, The Two-Stream Convolutional Networks for Action Recognition in Videos, where they had an architecture taking, having they called the towers. The first tower took in the frames, and the first tower was intended to learn what it looked like, what the frame looked like. And the second tower had took in as input what they called optical flow. And shown below is how optical flow, which is a handcrafted or it's a computed feature where it takes it has information about the motion of the frame. And they, in their paper, Simonian and Zisserman used late fusion to take the outputs of the two towers and then merge it into one layer to have a classification for the classes. Okay. Now, the late fusion concept was actually introduced by Karpathy in his paper Large Scale Video Classification in 2014, where he also talked about different ways of fusing multi-stream architecture. So the single frame just took in like a lot of frames, compressed one frame, and then you run it there, and then the architecture learned from each frame. Late fusion, you take two frames, certain time apart, each learned, and then they're fused at the end. Early fusion, you take a lot of frames as input, like a volume, feed it through, and then it classifies the volume. And finally, slow fusion, where it takes as input different segments of a video stream and learns a little from each segment and then fuses it, but slowly, unlike with late fusion. So that's just, FYI. We'll talk about that later. In a paper by Fichtenhofer and company entitled Convolutional Two-Stream Networks, they studied um, different methods of what to fuse between two architectures, how to fuse it, and where to fuse it. We've seen where to fuse it in previously, where you can have it at the end, at the beginning, or somewhere in the middle. But things like, what do you fuse? What do you fuse? You know, um, you can have some architectures may have different inputs. So how do you fuse them? How to fuse them? Do you just join the two as do you just concatenate the inputs, or do you do some max pooling? Or so they studied all those. And where to fuse it, well, they talked about where to fuse. And what their findings essentially is that the parameters to these questions affect performance. Okay. Uh, in another paper by Fichtenhofer and with different set of researchers, in a paper entitled Spatial Temporal Residual Networks for Video Action Recognition, instead of using convolutional networks, they use residual networks. And from fusing different streams, they just connected them using residual connections, as shown by this red uh, residual connection. And they demonstrated that the residual connections between streams improved previous state of the art in the context of video action recognition. Okay, and then also by Fichtenhofer, you can see he's a very productive researcher. They did with a set of other researchers in a title "Slow Fast Networks for Video Recognition" in 2018. They tried having different frame rates for the, so you'd have one stream taking low frame rates, meaning it takes like every X number of an X is relative large number, so maybe every 8 frames as input, and you have a high frame rate tower where it's faster, maybe it's every 1 or every 2 frames as input, and then they fuse them. And well, their finding was essentially that having different frame rates as inputs may improve performance of your architecture with respect to video recognition. So let's now go to the, wait, how do I scroll this paper? Whoop. Okay. Well, now let's, to summarize so what I've just said, the background. So we have the two-stream hypothesis, which that for video, the human brain processes objects and the movement separately. This two streams network, that two-stream networks work. This was proven by Simonian and Zisserman. The residual connections between streams and the blocks work, and having different video frame rates may improve performance. Okay, so which brings us to the topic of this paper. The research question is: so what's the best way to combine appearance and motion, and how and where should different modalities interchange representation? So the question is basically, given, let's say, X number of towers, how would they, where do you put the residual connections, or how should they interconnect? Should they interconnect in the middle, in the end, or in the beginning, or what? So the paper solution is what they termed a new multi-stream neural architecture search algorithm with connection learning guided evolution, which focuses on finding higher level connectivity between network blocks taking multiple input streams at different temporal resolutions. In simpler terms, so given network blocks taking multiple input streams, so each network block can take either both motion and appearance, or maybe one of them, or maybe different motion inputs but at different frame rates. And how do you connect them? So their answer is a new multi-stream neural architecture search algorithm. So that's what the paper is really about. So what they did is that they modeled an architecture as a graph and network blocks as nodes and their connections as edges. To give you an idea, so if you had different network blocks parameterized by, with respect to this paper, C and R, which are number of convolutional filters for C, and R is the temporal dilation. I'll talk about that later. And input, RGB, and flow. How do you connect them? And what does that mean? How do you connect them? Well, to show you to um, so what they did was that so they had the different network blocks, and they had the network blocks were interconnected like this in the leftmost figure, and then they evolved it, taking connections, trying different connections, processing the blocks could be by splitting them or merging them, and so on until they arrived at a higher fitness, in this case 64.02, rather than better figure than when they first started at 60.68. So that's a 4 point increase in improvement in fitness. By fitness, I mean accuracy of classification. Okay. So just to give you an overview of what happens in the experiments, how things evolve. Okay, so let's talk about a network block first. So a network block is composed of a stack of M of 2D module and 2 plus D modules. Uh, so this repeated n times. So this is a 2D module. If you can see my mouse, this is a 2 plus 1D module. We stacked it, and m times of this is one network block, parameterized by C, which is the output channel size, and R, the temporal resolution. So they're blocks. That's what each of these small blocks are. Okay. And uh, the temporal resolution I was talking about is essentially they're trying to simulate having different frame rates. So in a paper, they called it temporally dilated 1D convolution. So a 2 plus 1 module, 2 plus 1D module is composed of a 1D temporal, 1D convolutional layer of size. So this is a 2 plus 1D module. And I think this is the temporal 1D convolution layer. And what that does is, okay, it tries to simulate having faster or slower frame rates. In a paper called, in a paper by Yu et al., they in a paper entitled "Multiscale Context Aggregation by Dilated Convolutions" in 2016, what they did was that they proposed this technique of expanding the receptive fields by you can see here. So if you had pixels here, they spread them apart so to lower resolution, and they put in zeros, I think, in the spaces. So you can see it's being dilated. So you could in the paper for temporal, it's like you're skipping frames. Diba? Parang it's like you're putting zero where information from a frame would be. Okay, I hope that was clear. So the temporally dilated one-dimensional convolution, the equation was this, which was just similar to the dilated convolution in 2D space. So it's just an analogy that they used. Okay. So let's talk about the architecture, their neural architecture search algorithm. I blurred out the details so I can talk about so you can you can appreciate the bigger picture first. So they began with an initial population of architectures. Let's call them G1, G2, G3, up to GP. In later details, we'll see that P in their experiments they used P, I think was 20. So they had 20 architectures like the one seen here. So they generated an initial population, and they used the tournament selection algorithm, where for each evolution round, you choose a parent architecture which has the best fitness in a subset. So you choose maybe 5 of 20. So given 20 Gs, 20 graphs, 20 architectures, you choose 5 randomly, and then choose the best one, and you call this the parent. Now this parent, you mutate it into a child, and then you add the child to the population. So, and then you discard the one in the population which has the worst performance. So it similar to evolution. In evolution, diba? In evolution, it's survival of the fittest. So you take in a population in evolution, you take a parent, it has children. If the children perform better than the parent, so the model replaces the parent with a child and then eliminates the weakest. So you can think of it that way. And then the strongest parent again has children. The children replace the parent, and the weakest of the herd, gets eliminated. So that's the concept behind it. So to talk about, let me just now talk about the details of each step. So begin the population with a certain number of p. So in this case, they start with p equals 20, and for each architecture, to prepare an architecture, they prepare a fixed number of stems or source nodes. In this case, are these two RGB and flow, and nodes at each level. So they have blocks. They start with blocks, and there are 4 levels. So I think one, two, three, four. 1, 2, 3, 4. They count. I think the first one is 0. Okay. So to have a initial population, you start off with a set of architectures, and then you mutate them, just to have randomness of parents, starting parents. Okay. So these are the details. Apply a number of split and merge mutation operations, and then randomly connect nodes with probability 0 0.5, discarding architectures with graphs of depth less than 4. This doesn't make sense. This didn't make sense to me actually, because they started out with 4 levels, and they didn't have a step where they eliminated levels. Okay. And then to choose a parent architecture, so you randomly sample a subset of the entire population P prime. So you take, let's say, 5 from the 20, you take 5, and compute the architecture with the highest fitness, so, or video classification accuracy. So you take the 5, you take the best performing, mutate this into a child architecture, and you mutate this using what they called connection learning guided evolution. Apply a random number of mutation operators on it, to kind of simulate changes, and then add the child to the population, and then discard the model with the least fitness. So this algorithm is their main contribution. Okay, so some details. What does it mean that they connection learning guided mutation? This is when they mutated a parent into a child. So they took the architecture and changed the different connections. And how they did it was that for an architecture, they maintained the high weight connections and then replaced the low weight connections with new random ones. And splitting and merging is essentially, they allowed splitting and merging. Split is to split one node into 2, but maintain the total number of parameters. So to do this, they just half the size of the channels of the original node. So into 2. So uh, architecture divides into 2, and the channels are now half of the parent. So total number of parameters still fixed. And the merging is just the other way. So when you're merging 2 nodes, you just add their channels, total channels, and the temporal dilation rate is randomly chosen between the 2. Okay. So they experimented on the Charades data set, which I showed some samples of. So the Charades data set is about 10,000 videos, 157 classes, and each video having about 30 seconds. And this is very challenging due to the duration and variety of activities. So you may have activities which overlap in time, requiring the model predict multiple class labels per video. And this moment in time data set, which has about 800,000 videos running about 3 seconds each. But the difficulty here is that, again, the same action may have different concepts. So some experimental details, how they prepare the initial architecture, okay, and how they measured fitness, which is by So they trained each model for 10,000 iterations, measured its top 1 and top 5 accuracy, and then added it, and that's its fitness. So they ran it. These are the results. So um, well, they outperformed everybody, but it's only surprisingly it's only at 58.6. So there's still a lot of room in video recognition. There's still a lot of improvement that can be done in video recognition. So just taking a look at the top one, for example, for the moments in time, it's only at 34%. So we're still way behind then. There's still a lot of room. Okay, so they also compared their algorithm, their search with other kinds of search models, and they came out better than the other. The other two, they compared it with standard evolution. Uh, I don't remember the details, or just randomly evolving, meaning I think they just, okay. And more results. So they compared AssembleNet and architectures without evolution, but with connection weight learning to see, how what kind of effects, marginal improvements that their techniques contributed. Okay, so moving on. So the general findings were, some connections were non-obvious and non-intuitive. They didn't explain why it would be non-obvious or non. Maybe because they allowed connections to jump layers. Okay. Marginal findings. There's more than one possible connectivity solution which can yield similarly good results. So there could be many solutions. Their their search algorithm could yield many similar solutions, or many solutions which yielded similar results. Okay, so models with random connectivity performed poorly compared to AssembleNet. So what they're saying is that AssembleNet does a very good systematic way of searching for the best solution over, random. Okay. So other observations, this always have only one block at the highest level, although authors allow the search to consider having more than one block at that level. Okay. So in conclusion, the authors present AssembleNet, a new approach for neural architectural search for using learning guided architecture evolution. AssembleNet finds multi-stream architectures with better connectivity and temporal resolution for video representation learning, and experiments confirm that the learned models significantly outperform models on two challenging benchmarks/datasets. So other details. So this is what the super graph would look like. This is the space where all possible connections are in. So all the other models that we've seen are subsets in terms of connection, subset of this big architecture. Just to give you an idea of the search space. Okay, and that ends my presentation. Thank you very much. Any questions?
Question. Um, so I imagine what they're trying to do is use some kind of evolutionary algorithm to experiment um, with the connections
Sorry?
of the yes the connections of the layers. So have they tried other evolutionary algorithms
Yeah.
like genetic
Yes.
genetic GE IGA, genetic algo, differential evolution, and etc.
Okay. No, they didn't talk about that. They did mention a paper from where. Oh, wait, sorry. Okay. They took their algorithm from. Wait, where did this overview? Uh, Here, Goldberg and Deb, 1991. So this paper presents several other selection algorithms, but I didn't really read the paper anymore.
Okay. Uh,
But the paper, this paper in particular, AssembleNet, the paper AssembleNet, no, they didn't show any other except for the random evolution, which they did, and what was the other one? Hold on, standard evolution, which to be honest, I didn't pay attention to anymore.
okay. Just because I just asked that because I think the paper could use some, could use other types of evolutionary learning,
Yeah,
because obviously you saw the super space of all the possible connections, and then you will experiment with the combinations of the connections, etc. You want to cut down on the other solutions. Like for example, you said that they also noticed unnecessary connections, right? So if you want to speed up the time, obviously that experimentation takes very long time, because
yeah,
you want to experiment on various models before you perform the tournament selection, right? So yeah,
yeah.
I thought maybe they tried other evolutionary algos, but I guess that's possible for
That's a
future.
paper you could work on.
Yeah, yeah, it's a possible future research. Yeah.
Future
So
work. Yeah.
yeah, yeah, yeah.
Thank you. Yes, thank you for that insight. Okay, I guess we're done.
I have a question for you, Roland.
Yeah.
But maybe not very related to the technical details of this paper.
Uh
But
huh.
did they mention something about how more complex this method would be compared to the other multi-stream or other video networks architectures?
Okay, so your question is how complex is this compared to others I've seen?
Yeah, parang in relation to it being NAS, when you're an architecture
Uh
search,
huh.
because I don't really have experience on, so if you could
Actually,
say
I don't,
something.
I don't, I don't either. I tried looking into the other papers on NAS is just random. One was randomly connected. I forgot the name of the paper, but it was for image recognition. And then the other one, I forgot the other paper, but I'm not familiar with the extents. I'm not extensively familiar with the literature on
Mm-hmm.
NAS.
Okay.
But actually, I wanted to, if I had more time, I'd look into the different other algorithms and other search methods. So thank you for that.